This lesson is going to be on finding the average rate of change of polar functions. So, everything we've done or everything we're learning in this lesson is something that you have already learned with other types of functions. So, hopefully, it's going to seem familiar. I am going to do the work on the calculator. I cannot promise you that you won't have to do this by hand on the exam, but you already know how to plug these values in by hand. We've done it tons of times um, so far in this unit, so we're just going to use the calculator here because I know you can do it the other way. In previous units, we've learned about average rate of change of a function in rectangular coordinates. In the polar coordinate system, we will find the average rate of change of r with respect to theta over a given interval of theta. All right, it is the same exact formula that we learned earlier in the year and have practiced it with many types of functions. You're going to, if your interval is from A to B, you're going to do f of B minus f of A in the numerator and then B minus A in the denominator. It is important you understand what we're doing geometrically. Geometrically, the average rate of change indicates the rate at which the radius is changing per radian. All right, so let's look at example 1. We're going to consider the graph of the polar function where r is equal to f of theta and f of theta is 3 minus 3 cosine of theta in the polar coordinate system. So I hope that you recognize that is going to be a cardioid. It's going to be sideways. Cardioid is basically going to look like something like that. We don't have to know that to be able to do this problem, though. That's just some extra information. So what we're going to do is find the average rate of change of r over the interval from pi over 2 to pi. So as long as your calculator is in polar mode, we can go to y equals, and it's actually r equals. And we'll just type this in. All right, and then go back to the home screen. And I'm going to go ahead and write what we're going to end up doing. I recommend that you write this because there aren't going to be average rate of change polar problems on the free response, but there will be rectangular equations that we do this. So I think it's good practice that you write what you're actually going to do. You're going to do f of pi minus f of pi over 2 in the numerator. And then in the denominator, we're going to do pi minus pi over 2. Okay, so what we would do on the home screen is go ahead and get our fraction bar. And then we just put that function into R1. And so this is kind of cool. Where we used to go to get Y1, if we do alpha trace, our choices are R. That sounds weird. So they're in R1. So we'll do R1 of pi, which is second, and then a little caret. All right, and then we'll do alpha trace and get R1. And then in parentheses, we'll do pi over 2. All right, and then in the denominator, we're going to do pi minus pi over 2. And there it is. That is going to be our average rate of change. It is approximately 1.910. We technically could do 1.909, and that is 100% correct too. So truncating or rounding are both perfect. All right, this next question, it's kind of difficult to do if you use the graph. So the graph feels like the slope is going to be 0. Like this is pi over 4, and this is 3 pi over 4. And that looks like that is a slope of 0, but polar slopes and polar average rates of change don't translate the same way as rectangular. Because maybe this point over here, r is technically -3, and that's a change of 6 to go from 3 to -3. So I'm going to actually, on this problem, just ignore that graph and just let my calculator figure it all out for me. So this is the graph of the rows. That is 3 sine of 2 theta, so 4 petals. They have a length of 3. The first petal is at the angle of pi over 4. But again, we really don't need the graph to do this problem. What we need to do is if we go to y equals, that is going to be r equals, and then we'll do 3 sine of 2 theta. And we want to know which one of these is 0. And it feels like A is going to be the answer, but when we try it, I'm going to go up here and close these parentheses because that might mess up. So it's not it. That's not going to be 0. And so what you would need to do is just keep trying these choices until you get the choice that is 0. Now I already know what it is, so to save some time, I am going to go straight to the answer. It is Brian Passwater's favorite answer, which is C. But let's just double check that I didn't do something wrong. So we'll do 7 pi, or r of 7 pi over 4 minus, it's technically f of, but in the calculator it's r of. I just saw a mistake I made typing it in, so we'll go back and fix that. So I think if I don't do these parentheses here, it will mess up. Okay, let's see. There we go. There's our 0. All right. All right, and then this next question, we have to use the graph because we're not given the function. So for example 3, in the polar coordinate system, the graph of a polar function, r equals f theta, is shown with a domain of all real values theta between 0 and 2 pi on this interval of theta. The graph has no holes, passes through each point exactly one time, and theta increase. And as theta increases, the graph passes through the label points A, B, C, D in that order. So that kind of takes away that issue that we had on this one. If we were using the graph to find the rate of change, this one we don't have to worry about negative r's. It's going through here at each one of those angles as you go around. The r value is where the point is. So that has to happen for us to really use the graph to get the answer. Okay. On which of the following intervals is the average rate of change of r with respect to theta the least? Okay. And so let's think about from A to B. From A to B is here to here. So r is like between, looks like between 2 and 3. And then between 2 and 3 again. So the r hasn't changed. So there is no change. Sorry, I said that 3 times. And if r doesn't change, the average rate of change is 0. Right, so that's going to help us in a second when we figure out which one is the least. Okay, then when we go from B to C, the R is changing from something between 2 and 5, or 2 and 3, like 2.5, to something between, looks like between 5 and 6. So the R is getting bigger. R is increasing. So that would mean the average rate of change is going to be positive. Okay, and the next question from C to D. C to D, R is not changing. Which means the average rate of change is going to be 0. And then from D to A, the R value is shrinking, is decreasing. So the average rate of change is going to be negative. So this question asks which one has the least value for the average rate of change. So the least value is going to have to correspond with the negative R, or the negative rate of change, sorry. All right, and then the last example, we're going to be estimating values using the average rate of change. So for any given interval, we can use the average rate of change over an interval to estimate other values of the function inside that given interval. So we're going to recall something, and I looked it up. It is actually from lesson 4.3. All right, and actually this is a little bit different on your paper than it is on mine. I made a change but didn't change this. Okay, so this is actually point slope form, but when we used it in lesson 4.3, we used this version. I'm going to go back and show you because I remembered it. I didn't remember it. I had to go back and look and see what lesson it was in. All right, so here it is. That linear functions have a constant rate of change, and that constant rate of change is called the slope. And we can use this to give our function where x1, y1 is any point on the line. All right, so we're going to use that. Here. But instead of x and y, we're going to have theta and r. So we would have that r is equal to r1 plus m. And what we're going to do is use the average rate of change as our slope. And then this is going to be theta minus theta sub 1. So when we do these problems, for this one example, we could use this theta and this r that goes with it, or we could use this theta and this r that goes with it. And when I was looking at lesson 4.3, I saw that on those we gave two answers. You could give two answers. So same thing here. There could be two answers. All right, so this can, since r is f of theta, we could also write it that way. All right, so this theta and this r, or this f of theta, are the actual variables. And then theta sub 1 and r sub 1 are going to be points from the table. And we can use that to approximate any value. So in here, we're going to approximate this one as long as it's within the interval. Now, the best approximation is going to be the one that's closer to, like, if we were going to do this one, we would want to have our theta sub 1 to be the one closer to it, but it's fine. We're just going to give an approximation. It doesn't say to give the best approximation in this course. All right, so let's do this. What we need to do, and this is the same thing we did back in Unit 4, is we want to find the slope, or we want to find the average rate of change. This is going to be an approximation of the slope, where we're going to subtract the y coordinates in the numerator. So I'm going to keep with the order we've been doing it. and this would be -1 minus 2. If you wanted to write it as f of 7 pi over 6 minus f of pi over 6, that's fine. And then the denominator will subtract the angles. Okay, so I am just going to let my calculator do this math. Again, I cannot promise you that you won't have to do this by hand, but I have complete faith in you that you can do this by hand. Oops, got two minuses going on. Okay, so most likely on these, because we're subtracting pi's in the denominator, you're going to get some ugly decimal. And I want you guys to remember that you only round once. Not YOLO, your row. You only round once. And so what we're going to do, so I don't have to keep writing that whole thing out, we're going to store this in the calculator. And I'm just going to go ahead and call it M. All right, so just a refresher on how you store things in the calculator. You hit the store button that's right beside the 1, and it's going to take the last thing we had. And then to get M, it looks like it is alpha and then the division to get M. All right, so now if I hit M, that's the number I'm going to get, and I'll need that in just a second. Okay, so let's finish the work for this problem. We're going to use that green formula, or possibly either one of those green formulas. I'm going to go ahead and use the one with f of theta. It's going to be equal to our R1. So you guys get to decide which one of these we're going to use. Now, when I did it before, I used this first one. So this was my theta 1, and this was my R1. So that was 2 plus, and then I'm just going to write M because I don't want to write out that ugly decimal, and then theta minus, and then our theta 1, which is pi over 6. Okay, so that is an equation for that function. That's an approximation. And then what I want to do is I want to approximate it for 5 pi over 6. This is the problem we're going to get to. So what I would do is I would take that 5 pi over 6 and I would put it in for theta. And that's going to give us an approximation for it. It might be a good one. It might be a terrible one. We don't know a ton about this function, so it doesn't really matter. All right, so this is what I'm going to do. I'm going to go to my calculator, and I'm just going to type this in, 2 plus M, which is alpha division, and then in parentheses 5 pi over 6 minus pi over 6. And I get that it's approximately 0. Now, don't be surprised if it doesn't come out as 0. You get decimal answers, it's fine. But I just want you to know that each one of these are going to have 2 possible solutions. However, you only have to find one. Don't worry about finding both the solutions. So there are 2 possible solutions, but you only need to find one of them. But when you check your answer, you'll see 2 answer choices.